Okay, so shall we restart? So I defined a bunch of restricted domains, well, that are fundamentally one-dimensional. So single-peaked, single-crossing, and one Euclidean that is one-dimensional even in a kind of formal technical sense. Okay, so let me now define something that is more interesting in the sense of not being one-dimensional. So let me define the domain of preference that are single-peaked on trees. Okay, so this is a slightly ugly definition. So let me give it anyway and then try to explain why it makes sense. So we say that a profile over a candidate set C is single-peaked on a tree if there is a mapping that maps candidates to the vertices of the tree, kind of placing candidates at vertices, so that for each voter, his or her preferences are single-peaked on every path in that tree. Okay, so here's how I would describe it differently. So this is the formal definition. It's also nice. An equivalent definition and maybe more intuitive is actually in terms of contiguous segments. So preferences are single-peaked on a tree if for every segment of voters' preferences, that segment forms a contiguous subtree. Right? And yet another way to think of it is, okay, so I have this tree. So here's how I can describe voters' preferences. So a voter has his top choice, say here. Now suppose I take this tree off the screen and make it hang off that point. Right? So then preferences should decline according to the force of gravity. Right? So along every branch, they decline according to the force of gravity. Right? So there's a top and they decline from the top. Right? And this is equivalent to every one of these definitions. So I'm not going to prove equivalence, but it's similar to the equivalence proof we did just for the line. Okay. So why should we care? Okay, decline along every branch, no valleys, right? So no valleys would be another equivalent definition. Yes? So? No, it's not rooted tree. But okay, so if you think of a specific voter and the top of that voter, you can make it rooted with respect to that root. But kind of in the definition, the tree is not rooted, right? So kind of like, it's more like every voter chooses his or her own root. Okay. So why are those good? Well, I claim that if voters' preferences are single-peaked on a tree, we can still have a Condorcet-Wiener. So again, we are guaranteed a Condorcet-Wiener if the number of voters is odd, and if it's even, well, we are not guaranteed a Condorcet-Wiener, but we are still guaranteed a weak Condorcet-Wiener. Okay, why is that the case? Well, let me actually prove that. So let me look at let me direct each edge according to the majority opinion, from the winner to the loser. Right, so like I do with the tournament graph, so I can do it with the tree. Right, so edges, so let me look at this one specific edge that I've directed, A to C. So I claim that there is a source, that there is a vertex with no incoming edges. Why? Well, basically because it's a tree, right? Right, so if you start at a leaf, either the leaf has this property that it has no incoming edges, or the leaf has incoming edges, and we cut off the leaves and continue, and eventually we'll get to a vertex with no incoming edges, right? Because there are no cycles, right? So because, well, okay, so another way to say it is look at these edges and follow them sort of upwards in the opposite order, kind of towards the root. And since there are no cycles, you'll have to stop somewhere. Okay, so there's a source. Like, okay, so it may be a weak source, right? So we direct each edge according to the weak majority opinion, so it can go both ways, but there will be a weak source, a node from which you can go in any direction. Okay, so I claim that this guy is actually a Condorcet-Wiener. So, okay, so what do I know about him? I know that he beats all of his immediate neighbors, or weakly beats all of his immediate neighbors, right? So that's by construction, by the choice of that node, right? So A weakly beats C because we have that arrow. So now, why is it the case that A also weakly beats, say, B? Okay, so suppose it doesn't, right? Okay, so who are the people? So let me think, okay, so why is it the case that A beats C? Right, it means that at least half of the voters sit in that subtree. So if A weakly beats C, if I cut my tree here, if I cut it like that, this means that I have at least half of the voters here. That's exactly what it means that A weakly prefers C. Because every voter who sits in that part of the tree, right? So if he's there, then as he goes to A, he passes through C. So C is on his way from his top choice to A. So therefore, his preferences must be declining, right? So the guys who are over there prefer C to A. The guys who are here prefer A to C, right? So this edge is sort of the divide between A over C voters and C over A voters. So I have at least half of the voters who sit here, right? And all of these voters, of course, prefer A to D, A to B, A to all these other guys, right? And similarly for every edge adjacent to A, right? So if I cut that edge, then the part containing A contains at least half of the voters. So A is preferred to everyone in the cutoff, to everything in the cutoff part. And since I can cut off every part, so A is preferred to everything. Okay, so that's the argument. Okay, so now if I have preferences single peaked on a tree, it's not true that the weak majority relation is necessarily transitive. So I don't quite have that, but at least, at least I have weak condensationers, right? And that's already something, because for general preferences, we are not even guaranteed weak condensationers, right? So that's also an interesting domain. Okay, let's see some special cases. So when the tree degenerates to a line, of course, we recover our usual definition of being single peaked on a line, right? Because that's just that. Being single peaked on every path in that tree. If the tree itself is a path, then just that. Okay, so what if my tree is a star? So I have it in the slides, but I want you to think about it. So what does it mean that preferences are single peaked on a star? So this is the star. So this is the central node, A, B, C, D, E, whatever. So what does it mean that preferences are single peaked here? Okay, so suppose you have a voter who ranks E first. Which candidate does he rank second? A, right? So if he ranks any leaf first, he ranks A second, and after that he can rank the remaining leaves in any order, right? So there are no constraints coming from the tree structure. Suppose he ranks A first, then he ranks A first, and then everything else can come in any order, right? So basically, so this is a characterization. There exists a special candidate ranked first or second by every voter, right? So this is exactly when preference is single peaked on a star, right? That's a characterization, right? And that in particular tells you that this is not a very, very strong restriction that preference is single peaked on a tree, right? Because basically, okay, so what can you do? You can take an arbitrary profile, introduce a dummy candidate, put him on the first position in every vote, you get preference single peaked on a star, right? So if there was a complete mess among all the candidates other than dummy candidate, I mean, that complete mess is still there, right? So you don't have an awful lot of structure. But kind of having that one candidate who is on top makes it single peaked on a tree, namely a star. And of course, it gives you a condensationner because this new dummy candidate would be the condensationner. Okay. So this is a very rich domain. So sort of it's surprising that we have some positive results for it, but we do. So I'll talk about that, I think, tomorrow. Okay, so now the question of recognition. Okay, so it's easy to check if a profile is single peaked with respect to a given axis, right? So you check contiguous segments, for instance, right? That's the easiest option. It's easy to check if a profile is single crossing with respect to a given order of voters. Okay, annoying but easy. So you take every pair of candidates and you check kind of when they cross. So quadratic in the number of candidates, order of m squared n roughly. It's easy to check if a profile is one Euclidean for a given embedding in the line, right? So you measure the distances, right? So you see if the profile is consistent with that. Or single peaked on a given labeled tree, right? So if you label the verts of a tree with candidates, it's easy to check if a profile is single peaked with respect to that. Okay, so these are the easy questions. So here are interesting questions, non-trivial questions. Can we efficiently check if a profile is single peaked with respect to some axis? Now the game is, you are given a profile, you suspect that it's single peaked, but you don't know the axis. Can you check if it's actually single peaked for some axis? Can you generate that axis? So same question for single crossing, same question for Euclidean. Now for trees, we actually have two flavors of that question. First question is, you are given a tree, right? A specific tree like a star maybe, right? Or some more complex tree, but without a labeling. You ask if you can assign candidates to the vertices of that tree so that your profile is single peaked with respect to that label tree. There's also another question. So you're not given any tree, you're not given anything, you're just asking if your profile is single peaked with respect to some tree. Okay, so these are non-trivial questions, 5 of them. Out of those 5, 4 have polynomial time algorithms, 1 is NP hard. Okay, can you guys guess which one is NP hard? Just testing your intuition. Yeah, given tree, some labeling, this is NP hard. Right, so all others are easy, and we are basically going to see the easiness arguments, so either fully or some flavor of the easiness arguments kind of in the remaining time. Okay, so first a useful tool, right? And if you haven't seen it before, I think this may be one of the more useful things you learn from this lecture. Right, so this useful tool is the consecutive ones problem. Okay, how many people are familiar? Okay, quite a few. Okay, so for those who don't, do pay attention because it's fun. Okay, so here's the setup. You have a 0, 1 matrix. So the question is, can you reorder the columns of this matrix so that in each row, ones appear consecutively? Okay, so for instance, so here we have a matrix. Ones do not appear consecutively. So our job is to reorder the rows. So if you move, for instance, the blue row to the right, that will fix those ones but break those ones. So that's not quite the solution. So what we can do is to do this, right? So this is a reordering. Right? Move the entire kind of blue-orange block to the right. Right? And now it's contiguous. Okay, so this seems like a difficult task. It actually admits a polynomial time algorithm. Right? So it's one of those powerful kind of algorithmic techniques that you don't necessarily want to look inside, but you want to know that it works. Right? So this is something that we can do in polynomial time. Right? So if you're curious how you do it, so there's a data structure called PQ trees that sort of takes care of it. It's probably not something you want to implement, but it's known to be polynomial time. Okay, yeah, so if you ask me kind of in the coffee break, I can tell you some horror stories about implementation. Okay. Right. Okay, now this turns out to be extremely useful for recognizing single-peaked preferences. And here is how. So here's what I'm going to do. So I have my first voter. I'm going to figure out if, okay, so I have 5 candidates. I'm going to figure out if my candidates can be placed on a line to make that voter happy. So to make his preference a single peak. And then second voter, third voter, etc. Okay, so what does it make him happy? Well, these BA have to form a contiguous block, BAC have to form a contiguous block, BACD have to form a contiguous block, right? So I can encode it with zeros and ones, right? So here I'll say, okay, A and B have to be next to each other. So I'll have a column for A, B, C, D, and E, right? And it's intuitive, right? So we're permuting columns in consecutive ones problem, right? And when constructing the axis, we're looking for a permutation of candidates. So that makes sense. So here's how my encoding works. So I put ones in A and B, right? And that encodes that kind of column for B and column for A would have to be next to each other. I put ones for A, B, C, meaning these 3 columns should appear together. And I put ones for A, B, C, D, E. Okay, I'm done with this voter 1. So now voter 2 comes in, right? And this is his preference ordering. So I say now CD have to be together. So I put ones there. CDB, I put ones there. And CDBE, right? So I put ones there. Now third voter, I continue in the same fashion. Right, so here I got lucky because this particular preference profile is actually single peaked with respect to A, B, C, D, E. Right, so my matrix actually has consecutive ones property right away. So this is how I recognize single peaked preferences. Now I told you that to the best of my knowledge, there are no working implementations of this algorithm for consecutive ones. So it's more of a theoretical construct. Right, so when people actually have to do it, they end up solving ILP because even though ILPs are not polynomial, they're much easier to work with. Right, so this is sort of, okay, so this is polynomial time, but it relies on this black box. So can we have a direct polynomial algorithm? Right, so I say combinatorial, so people usually make difference between something that is solved by linear programming versus combinatorial. So I sort of abuse the term, I want to make a distinction between kind of solved by reduction to consecutive ones and solved directly. Okay. So let me give you a sort of a sketch of the argument. So again, I have this same profile. So what I do is I look at the 2 last positions in voters' preferences, right? And these last 2 positions are E and A, right? So these guys, E and A, are ranked last by some voter. So I know that they have to be at the endpoints of my axis. So I put them at the end, different ends. It doesn't matter which one. If one axis works, I can always turn it around. It would still work, right? So I put them at the different endpoints. And now I can delete them. Okay, so here's what I'm left with. Now again, I have 2 guys ranked last, D and B, right? Okay, so my life would be very easy if I could say I could put them in arbitrarily, kind of maybe D here and D here and B here or vice versa. Unfortunately, that doesn't work. I have to take care when placing these guys, right? But okay, so what do I know now? Now now that I know that B and D are kind of next, I know that C is in the center. Right, and what I can do now in this specific case, I know, let me look at voter 3. Voter 3 prefers E to B, yet E is not his stop. Right, so he prefers E to B. Right, so if E, okay, so he ranks E above B, but his stop is D, his stop is somewhere else. Right, so if D was here, so he would have to go D, B, E. Right, and we know that he prefers E to B. Right, so because so therefore D would have to be placed here. Right, so that he could have D, E, B. Right, so in this particular case, we could make this derivation. Right, so because we knew what's in the center, right, and so that told us how we actually have to place D and B. Right, so this seems like a hack. Right, so I figured it out in this particular case. Turns out that this is sort of a general argument. Right, so basically you can kind of, so your task is, okay, so at this point, your task is to place B and D. You try to figure out which restriction on placements of B and D you get from the votes, right? And these are restrictions of this sort, kind of contiguous segment type of restrictions. If you don't get any restrictions, you can place them arbitrarily. And if you get those restrictions, they actually tell you where to put B and where to put D. So you do that and you continue. Right, so I'm hand-waving this part because it would actually take another 10 minutes to explain properly. I'm not going to do that. But this actually can be done, and it gives you an algorithm that is both theoretically and practically more efficient than consecutive ones. Now, this algorithm has a nice history. So the way I learned about it was from 2018 ECI paper by Escoffier, Lang, and Osterg, right, where they claimed that to be an improvement to the Bartholdi trick algorithm from '86. Because it actually does have a better running time in terms of number of voters and candidates than Bartholdi trick than consecutive ones. Well, turned out that what they actually did is they rediscovered an algorithm from Journal of Algorithms by Dagnon and Fallman from '94, who proposed pretty much the same idea and the same running time. But the interesting thing about Dagnon and Fallman is that they framed their work not in the language of single-peaked, single-crossing preferences. Right? They talked about unidimensional unfoldings, and the application was something like mathematical psychology, like preferences not from the perspective of social choice, but from the perspective of trying to understand how people rank objects. Right? So there, apparently, single-peak, single-crossing preferences also make an appearance, except under completely different names. So if you Google for single-peak, single-crossing, you are not going to find that paper. Right? But that paper actually had this very elegant algorithm for kind of recognizing single-peaked profiles, finding kind of the single-peaked axis. Right, okay, 1994. So I'm telling you this story because we're going to come back to it. Okay, so that was recognizing single-peaked preferences. So we've seen a reduction to consecutive ones, and we've sort of seen a sketch of combinatorial algorithm. So let's try to do the same for single-crossing preferences. Okay, so again, we can do consecutive ones. So this is something that has been observed by Brederick, Chen, and Werkinger. And the observation, again, is it's not much different. It's not very different from single-peaked preferences. Now we are going to have a column for every voter, right? Because now we are reordering voters. So in that, and we are going to have a line for each ordered pair of candidates. So we'll have a line for AB, and we'll have a line for BA, two different lines. Right? That's perhaps the only subtlety of this construction. Okay, in the AB line, we have ones for voters who prefer A to B, because they have to be together as a block, right? So these ones have to be contiguous. They cannot be split by other voters, right? And in the BA line, we'll have ones for voters who prefer B to A, right? And with that simple trick, so we actually reduced our problem to consecutive ones, sort of by the same argument. So if we manage to arrange voters so that these ones are contiguous and the sort of BA ones are contiguous, then all voters who prefer A to B and all voters who prefer B to A appear in two contiguous blocks. Right, so that's exactly what we need. Okay. Yeah, the row intermatics, yes. Okay, so that works. So that actually is not super efficient, right? So you can actually do a little bit better than that combinatorially. Okay, so here's how you do it. And so for single crossing preferences, there's actually an algorithm that can be explained on one slide that is combinatorial, doesn't touch consecutive ones. So let me explain it to you, because I think it's also useful for intuition. Okay, so again, our old friend swap distance. Swap distance has made a lot of appearances kind of in our kind of discussion yesterday. It will also make an appearance tomorrow, right? So let's remind you. So the swap distance between two votes, the number of pairs of candidates on which these two votes differ, So let's assume all votes are distinct, because identical votes don't matter. If a profile with duplicate votes is single crossing, so the profile where these duplicates are sort of compressed into one is also single crossing. Right, so let's assume there are no duplicates. So here's a lemma. Suppose I have a single crossing order of voters, and in that order, U appears before V and V appears before W. Then I claim that swap distance from between U and V is strictly less than the swap distance between U and W. Right, so the swap distance sort of respects this ordering. Okay, why is that? Well, let's look at these three votes, U, V, W. Let's look at a pair of candidates that contributes to the swap distance between U and V. Right, so this is a pair AB on which U and V differ. Right, so it contributes to this count for UV. AB, BA. Well, can it be that in W we have AB? No, it won't be single crossing. Right, so therefore in W we also have BA. And therefore W and U also differ in that pair. Right, if U and V differ in that pair, then U and W differ in that pair. Right, so that pair contributes to the count for the UW as well. So whatever pair contributes to this count, so this pair then also contributes to this count. Okay, so this means that it's at least as large. Why is it strictly larger? Well, because all votes are distinct. If it's exactly the same pairs that they differ on, right, then V and W would have to be the same. Right, if it's exactly the same differences, right, so then these differences would actually describe how U and V differ, right, so there has to be something extra to make V and W different. Okay, so it's strictly less. Okay, that actually gives you an algorithm. Right, and the algorithm is like this. So we try to guess the first vote. When I say try to guess, we consider all possibilities for the first vote. And once we have that first vote, we order everything by the distance from that first vote. Okay, what can happen? So suppose we try to order by the distance and we have a tie. Right, then this set of voters cannot be single crossing with that first vote. Right, because here we just argued that there cannot be any ties. Right, so here we argued that if voters are ordered with U as a first vote, then distances are strictly increasing. So if there is a tie that was a bad guess for the first vote, we have to discard it and start again. Right? Suppose those distances are distinct, then it gives us an order of votes. Then it may or may not work. We still have to check. Right? So we have a candidate order of votes. We have to check. If it's single crossing, then it works. If it doesn't work, well, it was a bad guess for the first vote. But what we know is that if the preference is actually single crossing, then there is a correct first vote. And for that correct first vote, there will be an ordering of votes. So we are going to discover it in this fashion. Yeah? It doesn't have to be. They just have to be ordered in this way, right? Right, okay, so this is how I chose the pair AB. I chose the pair AB to be a pair that contributes to the difference between U and V. Right, so I said if a pair contributes here, it contributes there. So by construction, I'm only talking about pairs on which U and V differ. Right, so what I'm proving in fact, so I stated it as a lemma about distances. Maybe it would have been more instructive to state it as a lemma about sets. Right, so the lemma is the set of pairs in which U and V differ is a subset of the set of pairs on which U and W differ. Right, and the argument was if something is in one set, it's also in the other set. Right. Right, so if you look at these set differences in terms of pairs, right, so we have this chain of sets. Right, and we order the votes accordingly. So if it's single crossing, we are not going to miss it. Right, and if it's not single crossing, there is no way we can succeed. Right, so therefore this is an algorithm. Okay, so at least, so you can make it more efficient, right? So it has this kind of inefficient component of guessing the first vote. You can circumvent that, but for the ease of explanation, I decided to include it. Okay. Okay, so we try all possibilities for the first vote. Okay, one Euclidean preferences. Okay, so where is this algorithm from? Kind of this version. Okay, so I'm afraid that I have published that in a paper in 2012. At least we had the decency to think that because it's so simple, we are probably not the first people to discover it. So we said it's folklore. Okay, where did it first appear? Dagnon-Fallman. We didn't know. We suspected it was known, but yeah, so Dagnon-Fallman had that algorithm too. So I don't remember which name they had for single crossing, but they actually proposed even an optimized version of this algorithm, something that is slightly faster. Okay, so now we are moving to one Euclidean preferences. So the question now, can we recognize one Euclidean preference in polynomial type? Now the interesting part here is we don't even, a priori, it's not even obvious if this problem is in NP. Right? So because, well, your witness is an embedding into R, right? And for all you know, you cannot guarantee that this embedding comes with kind of small, nice rational numbers. Right? Maybe you only have a really ugly embedding with really large numbers. So a priori, it's not even obvious that it's in NP. But we are going to prove that it's actually polynomial time. Okay, we are not going to prove it properly, but I'll give you a sketch. So here's an observation. Suppose that we actually know the order of candidates. We don't know the, suppose that, okay, so we know the order of candidates, we don't know the order of voters, so we somehow guess the order of candidates, but then it suffices to solve a linear program. So the linear program will have variables for candidates and variable for voters, right? And this is what it says, right? So remember our counterexample for something that is single peak, single crossing, but not one Euclidean. Right, so we had these inequalities about how a voter is positioned with respect to the median point for pairs of alternatives. Right, so this is exactly what we do here. So if we have a voter and a pair of candidates A, B, such that in this order of candidate A is before B, then if our voter prefers A to B, we have an inequality saying V is to the left of the middle point, and if the voter prefers B to A, we have an inequality saying V is to the right of the middle point. Right, so we have to know the order of candidates, because without the order of candidates, we would have to deal with absolute values. Right, so if we don't know the order of candidates, then from this we can say our voter is closer to A than to B. Right, so the absolute value, his distance to A, is at most his distance to B. It's not a linear constraint. Right, but if we actually know the order of candidates, we can get rid of absolute values because we know which way they work. Right, and we can have linear constraints. Okay. So, and then once we have all these inequalities, if we have a feasible solution for this combination of linear inequalities, right, so then we have an embedding, right? Because if we satisfy all these constraints, then our preferences really are Euclidean, right? And if we don't, then we don't. So it's slightly annoying that we have strict inequalities, right? Strict inequalities are not good, right? But actually in this specific case, you can replace every strict inequality by non-strict inequality. Instead of saying less, we say less than equal than this plus 1. Right? We can sort of set the scale. Right? So think of our axis as being sort of made of rubber. You can pull at it to make sure that kind of all differences, all intervals are at least 1. Right? So you can safely have non-strict inequalities here. So the trick doesn't always work, but in this specific case it works. Right, so it becomes a standard LP with non-strict inequalities, so a solution is what we need. Okay. So now the question is, how do we get our hands on the order of candidates? Right, that's assuming we have an order of candidates. Okay, so that, by the way, proves that the problem is sort of in NP, right? Or at least we can solve it in M factorial type, right? So we can try all orders of candidates, and for each of them, we have to solve an LP. Right, so that gets rid of this sort of, infinite precision nonsense, right? We don't have to worry about that anymore. Right, so we know it's a solution to LP, so the numbers are nice and small. Okay, so where does the order of candidates come from? Well, what is the most natural place to get an order of candidates? Well, we have our input preference order, right? We have our input preference order, right? So the first thing we are trying to check if it's one Euclidean. As a first sanity check, we can check if it's single peaked and single crossing, right? We know how to do that. Right, I mean, if it's single peaked, right, in particular, that gives us an ordering of candidates, so we can use that order of candidate. Right, so, this idea is brilliant in its simplicity, but it actually makes our life very difficult down the line. So why? Because the single peaked order is not unique. Right, so there can be several, and here's the annoying bit. So you may have preferences that are single peaked with respect to several different axes, but only one of those axes works for the Euclidean algorithm. So for one of those axes, your preferences can be embedded. For others, they cannot be. And there can be lots of those axes. It can be, exponential in M. Right? So if you figure out one, you don't know if you figured out the right one. Right? So what this algorithm does, so this is an algorithm by Bick and Knobloch from 2010. She starts by guessing some axis, and then she may have to massage that axis to actually make things work. Right? So it's a complicated proof, and I didn't quite manage to get to the bottom of it. So Okay, so it's accepted in a decent journal, so I hope that the reviewers managed to check it, but I find it difficult to understand. Okay, so here's another idea which may seem counterintuitive. So, well, we can use, and this is an idea that was, let me be careful here, that was published in a paper of mine in 2014, and this is to use the unique single crossing order of voters. Okay, so what's great about single crossing of order of voters? It's unique. Right, so again, we can delete, duplicate, we don't care about reversals, so up to that, it's unique. Right, so why is it even useful? Why is the order of voters useful? Well, let's look at the first two guys, voter 1, voter n. Okay, so voter 1 and voter n, right, so they sit on the axis like that, right, so in particular, we know that voter 1 goes A, C, D, B, voter n goes B, D, C, A, right? And if we look at candidates F, E, then on those candidates, voter 1 and voter n agree. And on the candidates in the far end side, voter 1 and voter n agree as well. Right? So if we know that if on a pair of candidates, voter 1 and voter n disagree, that these are the candidates that sit in this middle part. Right? So at least we can identify this middle part and the order of candidates in that middle part. Right? So that gives us that. Okay, so what about those tails? Well, the tails seem to be harder to deal with, right? So there's a little bit more work to do. So in fact, in some cases, we may be unable to say whether candidate E should go here or he should go there. So both are consistent with our preference orders, right? But this is because if that happens, this means that we can actually work with either of those orderings, right? So this is something that works. Again, I'm not giving you full details, but this is actually a pretty simple argument. Kind of 5 more minutes, I could explain that. Okay. So from the single crossing order of voters, you get n ordering of candidates. So there may be several, but whichever one you take is fine. And with that order of candidates, you set up the linear program and then you're done. Right, so that's roughly the algorithm. Again, who discovered it first? Dagnon and Fallman, right? So in '94. Right, so that was the biggest embarrassment for us. Okay, so this is a paper from 2014. We knew of the story of 2008 paper of single peak preferences, who rediscovered that old paper. So we even tried to look at that old paper, found it difficult to read, right? And somehow it didn't occur to us that what we are doing here may also be contained there. Turns out that it was, right? So basically, okay, so that paper, kind of for all practical purposes, is non-existent because the results actually contained there. Right, so maybe if we have a nicer presentation, but all the ideas were actually in the old Dagnon-Fallman paper. Right, so yeah, so this is what happens when people write papers not using standard terminology. Their work can get lost. Right, so the way I actually learned about this paper, I got a very nice, friendly email from Pierre Dagnon asking me to explain the differences between the two papers. Right. All I could do was to apologize. Okay, so that's the story. Okay, so we talked about recognizing single peak preferences, single crossing preferences, Euclidean preferences. Let's talk about preference that's single peaked on trees. Okay, so I'm not going to give you algorithms, but let me at least tell you how the story goes. So there's an efficient algorithm that decides whether a given profile is single peaked on some tree, right? And that doesn't go by consecutive ones, right? So that works combinatorially. Again, with trees, you have an analog kind of to the line statement. A candidate can be ranked last, even only if it's a leaf, right? So again, by all these contiguous segment properties. So at the first step, you look at candidates who are ranked last, you decide that these are going to be your leaves, and you sort of build from there up. So it's not particularly complicated, but I'm not going to cover it. So it's a short, nice paper. It's actually well described by Michael Trick. So go ahead, read it. But here's the interesting part. It's hard to decide whether a given profile is single peaked on a given tree. So this is a surprisingly recent result by my student Dominic Peters and me, right? And in hindsight, it's a fairly obvious reduction from an exact cover by 3 sets. So let me give you the shape of the tree. The shape of the tree is like this. Okay, so the reduction from set cover goes like this. So basically, so you have the number, okay, so these are the elements of your ground set. So these are the guys that you want to cover, right, intuitively, right? And your sets will have to go here or there, right? So here you put sets that you choose to be in your cover, so that you actually have a nice exact cover by 3 sets, right? So actually, yeah, so I suppose. So I suppose an element, okay, no, it goes roughly like that. In the set that you are not using here, you put in those dummy vertices, and you have one more dummy vertex to take care of things. Right, so this is roughly how the reduction goes. So it's not a particularly complicated tree, so it's a tree of small diameter. Right, so this problem is NP hard even for trees of bounded diameter. So this degree is large, but you can sort of massage it slightly to make this degree bounded. So this problem is hard even for trees of bounded degree. So this is a hard problem. So it's hard to recognize a preference a single peak on a given tree. So in that same paper, there's a compact data structure that describes all trees on which a given profile is single peaked. So in particular, one question we can answer efficiently. So I want to find a tree with the smallest number of leaves on which my profile is single peaked. This is something I can do. This is something I can do efficiently, right? So I cannot decide for a specific tree, but I can find the tree that optimizes certain property, such as the number of leaves. So there's a bunch of other properties we can optimize using that data structure, right? So diameter would be one of them, degree I think as well, so a bunch of other things, right? So you can design nice trees, but you cannot obtain a specific tree necessarily. Okay, so that's the story with single peakedness on trees. So I'll tell you why it's interesting tomorrow. So it's actually nice applications for profiles that are single peaked on trees. Right, so it's sort of, so it's a data structure, so it's sort of hidden there, so you have to extract it from it.
But all possible
trees, yeah.
So which means that in some sense for the line also that becomes a special case.
Yeah.
Axis can be recovered.
Yes. Right, and so for the line it was sort of known, but yeah.
Okay, so is there, I was just curious for the line case, is there some kind of, some kind of a relationship between the two different axes for which a given profile is single peak, let's say. So there may be multiple axes on which a given profile may be single peak, but given a particular axis, can I transform, to another axis? Is there some kind of, result known?
Right.
By some kind of, transformation actually.
So this is something, so you can sometimes, okay, so not universally, so this is something, for instance, that Knobloch does in her algorithm. So kind of a base step would be to take a chunk of the axis, flip it, and put it on the other side of the axis, and there are conditions when this is something you can do. Right, but kind of generally, so I'm not sure how to phrase it properly. So if you ask if one axis, if there's a profile that is single peaked with respect to both axes, that's easier to answer without transforming the axis. Right, so if you want to count axes for which a given profile is single peaked, you can. So you can get not just a bound, but you can get an exact number. But kind of anything more explicit, I don't know. So I'm not sure how to ask that question formally.
So another thing I was curious is, for example, this one-dimensional embedding which we talked about for single piece and single crossing. So is there higher dimensional embedding also?
Yes, they are, but they're hard. Okay, so I was planning to mention it briefly. I might as well talk about it now. But yes, it's indeed a very natural question. Maybe I should have mentioned it earlier. Right, you can also embed voters and candidates in 2D. Right, and then also preferences would be driven by distances. Right, so it seems like a reasonable domain restriction. You can actually show that not all preferences have this property, so it's a meaningful restriction. Right, so it's not that easy to show actually that something is not 2D Euclidean, but I mean, you can do that. Right, so there are ways to show it. Right, so by the way, so everything is Euclidean if you allow yourself high enough dimension. Right, so the easiest way to see it is you have an axis for each candidate. Right, and then each voter kind of, you shift it a little bit, you put it in the point 1, 1, 1, 1, for instance, and you shift him a little bit in each direction according to which candidate he likes more or less. Right, so in that way, everything is Euclidean. Right, not everything is two-dimensional Euclidean, and it's hard to decide what is. And hard is not NP hard, it's beyond NP hard. It's one of those hardness classes that deal with reals. Right, and that's a paper by same guy, Dominic Peters, single author paper, from I think a year ago, right? So he provides that hardness result. So it's sort of, the reduction itself is easy when you know what you're reducing from. It's kind of finding sort of the right geometric problem to reduce from that is interesting. Right, but yeah, so, and also what is not known if kind of two-dimensional Euclidean preferences are useful for anything. Right, so it's restrictive, all right, but one-dimensional preferences are kind of algorithmically useful and social choice useful, right? So we've seen social choice usefulness like condursiveness, sensitivity of majority preferences, all that stuff. None of that holds in 2 dimensions. You can embed condursive cycle in 2 dimensions, right? So it's not nice. So potentially it would be used for kind of algorithmic purposes, but we don't know how, right? So this is something I hope someone will establish one day, how to do something general NP hard efficiently in 2-dimensional Euclidean preferences. I think such examples may exist, but yes, I haven't worked on that hard enough, but I think something like that might work, right? But at this point, it's pure speculation. No such results are known. So I think so. There's a paper by Anna Bogamolna and Jean-François Lallier, which I think basically says that you need something linear in the number of candidates. I think you cannot get away with logarithmic, but maybe I'm misinterpreting the results. But so it's, I mean, so it's not quite a counting argument, but something of that fashion. Right? So yeah, so large. Okay. So yeah, so I promised applications. So let's talk about applications. So yeah, okay. Sorry? So this is a paper, so it's called Edith Elkind. So I think nice trees we have in the title of that paper. So I'm not sure about the conference, but I mean, so we maybe have 2 drawing papers that year or 3, not more than that. It has nice trees in the title, right? So something about preferences. I think it's something like preferences single peaked on nice trees. So the data structure is in there. Okay. Okay, applications. So I claim that single peaked, single cross. Okay, so ultimately, when we have preferences, we typically want to aggregate them, right? So kind of voting is about aggregating preferences, right? So not just kind of marveling at them, how beautiful they are, but actually, you know, making collective decisions, right? And making collective decisions, so that's voting rules, right? So the single winner rules whose output is hard to compute, right? So do these become easier if we have single peaked or single crossing preferences? Well, okay. So there are rules of the form that say, okay, if there is a condursive winner, output it. If there is no condursive winner, do something complicated, right? So Dodson rule is kind of like that. If there is a condursive winner, right, we can output just that. If there is no condursive winner, we have to compute those kind of Dodson scores based on swap distances. So there's another rule like that that I didn't really define. It's called Young's rule. On the Young's rule, again, you try to make a candidate a condursive winner by deleting voters. So you ask how many of your voters you have to shoot to make that guy a condursive winner, right? So kind of not very nice voting rule, right? Well, disenfranchising them is better than shooting them, but still, right? Okay, so every candidate can be made a weak condursive winner by shooting off everyone, right? So for everyone, Young's score is well defined, right? Weak condursive winner. Not everyone can be made strong condursive winner, so yeah. Anyway. Right, so for that, again, so if there's a condursive winner, we output it. If there's no condursive winner, so yes, how many people do I have to shoot to make that guy condursive winner? Right, so that's again NP hard to figure out. Right, it's not that easy to find exactly the right people to shoot. Okay, so if preference is single peaked on a tree or single crossing, and the number of voters is odd, then with these rules we're actually done, right? Because we're in the first part. We're in the part if there's a condursive winner. Because if preference is single peaked on a tree or single crossing and the number of voters is odd, we have a condursive winner. Okay, one has to be careful here. So what happens if the number of voters is even? Then we have a weak condursive winner. Now, what does Dodson rule say if we have a weak condursive winner? It doesn't say output all weak condursive winners. It still asks how many swaps do you have to make a given guy condursive winner, right? And it's plausible that for different weak condursive winners, the answer may be different, right? So some of these guys can be maybe made condursive winner with just one swap. For others, you may need more swaps, right? So not all of them have the same Dodson score. So you have to work harder, right? So in general, you may have to work pretty hard for general preferences, but if your preference is single peaked and the number of voters is even, right? So then you have this issue of distinguishing between weak condursive winners, but distinguishing between them can actually be done in polynomial time. Right, so you sort of use the fact that, okay, something you can prove that these weak condursive winners form a contiguous segment on your order. So in fact, we've sort of seen that in the argument I gave in the beginning of the lecture. Right, so these are the guys who sit between, left median voter and right median voter, voter k and voter k plus 1. Right, so all of those are weakened as winners, and based on that order, for each of them, you can figure out how many swaps you need. Right, so it's a nice little great algorithm. So that's from this paper, Brandbill, Hemasponder. Right, so this is something that can actually be done. Okay, so in fact, so surprisingly, it's actually, I'm not sure if it's known what happens if the number of voters is even and preference a single crossing. So I think Dominic and me had a chat about it, but I don't remember the answer. So if it's known, it's very recent, it's in a paper by Dominic, but quite plausibly it's not known. Okay. Okay, so another application. So that was single winner rules, right? So we had some examples. So in fact, so all hard single winner rules that we talked about, so like Dodson rule, Young rule, so you have this easiness result. Single transferable vote is an interesting case, right? So remember, single transferable vote, we have this issue of tie breaking. And if you want to have a neutral version of single transferable vote, right, then it's actually NP hard. So there's a claim by Dominic and Robert Brederick that this problem becomes polynomial time for single peak preferences. They've been trying to write down the proof for about half a year. Right? They keep finding bugs, but they haven't given up hope. Right? So stay tuned. Right? So that might be yet another easiness result. Right? So that will be nice if STV turns out to be easy for single peak preferences. Okay, so another application. So Kemeny rule. So remember Kemeny rule, this is our wonderful rule that minimizes the distance, finding ranking that minimizes the sum of distances to input rankings. Okay, so here's the claim. Suppose we have single peak preferences, right? Then majority preferences are transitive. So, okay, so here's the claim. If majority preferences are transitive, then Kemeny rule output the majority preferences. Right? So if when you aggregate collective preferences, you actually get not some kind of complex graph with cycles, but you actually get a nice linear order, then this is the linear order you should output under the Kemeny rule. Okay, why is that? Well, consider a pair AB. So suppose majority kind of has A before B, majority prefers A to B, so X voters prefer A to B, Y voters prefer B to A. Okay. So you have two options kind of in your output ordering for Kemeny. You can put A above B, you can put B above A. Right? If your ranking has A before B, right? So then you disagree with these Y voters, right? So you contribute Y to the score of that ranking. If you put B before A, then you contribute X to that ranking. Right? So it's in your, since X is small and you're trying to minimize the score, then it's in your best interest to agree with the ranking. Right? So individually on every pair, it's in your best interest to agree with the majority ranking on that pair. Right? So if the majority ranking is not transitive, you will not be able to agree with it on any pair. Right? So you'd have to disagree and you'd have to find a pair where to disagree. And this is where hardness comes from. But if you can disagree on it with every pair, right, and this kind of that's still transitive, then this is exactly what you should be doing. So if majority preferences are transitive, this is what Kemeny rule outputs. Right? And now a corollary to that, if you have single peak preferences with an odd number of voters, right, so then you have transitive preference and therefore you can compute Kemeny ranking easily. Right, so Kemeny also is easy for single peak preferences. Right, so single peak preference algorithmically useful. Okay, trick question. So suppose you have a single crossing preference with an odd number of candidates. So how do you compute Kemeny? Median voter. Right, so median voter has preference ranking that coincides with the majority, so you just output that. Okay, so there are a few more things you can do with single peak, single crossing preferences. So I'm not going to discuss it in any detail, so maybe some of that will actually come up in exercises. Okay, so I talked about equilibrium of plurality voting very briefly this morning. Right, so plurality voting has this super ugly equilibrium where you all vote for the bad guy. But if you have voters who are lazy or truth biased, you can actually do better. I didn't tell you how to find equilibrium in that case. So I had two slides where I had a characterization, which I didn't get a chance to show. Right? But that characterization basically reduces finding equilibrium to a hard problem. Right? Now that hard problem is hard in general, but it turns out to be easy for single peaked and single crossing preferences. Right, so for single peak, single crossing preferences, you can actually find sort of nicely structured equilibria for plurality voting, both for lazy voters and for truth-biased voters. Right, so that's a paper we had recently. Okay, so manipulation unfortunately also becomes easier with single peak preferences. Right, and control and bribery, which are other forms of dishonest behavior in elections that I'm going to talk about tomorrow, those also sometimes become easier for single peak, single crossing preferences. Right, and there's a series of papers with the results of that type. Okay, preference elicitation, right? So this is a beautiful topic. So suppose you know that your electorate has preference that are single peaked with respect to an axis. Maybe given axis, or maybe you don't know an axis, but you sort of expect the preference to be single peaked. How many queries do you need to figure out their complete preferences? Right, so same for Euclidean, same for single crossing. Right, so same potentially for single peaked on trees. Right, and it turns out that if you have this knowledge that preferences are single peaked or single crossing, you need many, many fewer queries. Right, so for single peaked and Euclidean, this is a paper by Vince Konitzer from quite a few years ago. For single crossing and single peaked on trees, so this is Palash Day and Nildara. And yeah, so I like both of these papers, especially the single crossing one. I think the single crossing one has a bunch of really, really pretty proofs. I'm hoping to cover some of them in the tutorial tomorrow, so maybe with Neil's help. Okay, so single peaked, single crossing preferences also make an appearance in resource allocation, interestingly. So there you can also talk about single peaked, single crossing. Right, and typically, but not always, they give you easiness results. Interestingly though, there are also some NP hardness results. Okay, so just a little bit about the history of this problem. So it was Toby Walsh who gave an invited talk at AAAI 2007, and he suggested that single peaked preferences may be algorithmically useful. That kind of hard voting related problems may become easy for single peaked preferences. But the only relevant result he had in associated paper, so he wrote a paper to go with his invited talk, was actually a negative result. So what he proved there is that STV with weighted votes remains hard for single peaked preferences. Right? So that was kind of a result that sort of didn't help him establish his claim that single peaked preferences may be useful, but in a way, kind of the claim still proved to be true, kind of by many other researchers, just not by the original paper that made this claim, interestingly enough. Okay, so that single peaked, single crossing preference. Okay, so here's one more story I'd like to tell you, so forbidden minors. Okay, so suppose in a profile, we have a voter who prefers A and C to B, so there's no good reason why C is not read, it really should be. Okay, so we have a voter who prefers both A and C to B. We have a voter who prefers B to A and C to A. And we have a voter who prefers A to C and B to C. So then this profile is not single peaked. Why? Okay, so if this profile was single peaked, then its restriction onto ABC would also be single peaked. Right? So if you delete voters from a single peaked profile, it remains single peaked. Right? And this restriction has 3 different guys ranked in the last position. Right? So therefore, this restriction is not single peaked. Okay, so this profile is not single peaked. Oh, there is a value for every potential axis. Okay, so now a somewhat more subtle story. Suppose you have a voter who prefers A and B to C and B to D, and another voter who prefers C and B to A and B to D. Now, this profile is also not single peaked. Right? And this is basically something you can do by considering all possibilities. Right? So who can be last? Right? Or valleys or whatever. Right? So it's kind of a small 2x4 profile. You can argue that for any of the 4 factorial possible axes, it's not single peaked. Okay. So the claim is that these 2 configurations completely describe single peaked profiles. So your profile is single peaked if neither of these configurations is present. Right, so basically, okay, so what do I mean by configuration? You can take your candidates, you can pick kind of okay, so for this configuration, you pick 3 voters, 3 candidates. For this configuration, you pick 2 voters, 4 candidates. Right, so you look at your profile, you pick 2 voters, 4 candidates, you rename them, and if you obtain kind of this sort of preferences, then your profile is not single peaked. But if no matter how you try to pick this 2x4, 3x3 minor, you don't get this configuration, then your profile is single peaked. Right? And that actually gives you an alternative algorithm for recognizing single peaked preferences. Right? So you just look at all these 3x3 and 2x4 minors. Right? So the running time is not great. Right? It would be like n cube, m cube, plus n squared times m to the 4th. Right? But it's polynomial time and it's very easy to describe. You just go through your preference and look for forbidden minors. Right, and it's a complete characterization. Okay, how do you write to this characterization? Basically, you try to run the combinatorial algorithm for recognizing single peaked preferences, and you ask yourself how you may get stuck. What may prevent you from completing this algorithm? And basically, you discover that the only thing that can prevent you from completing your algorithm are those bad configurations. So this is a similar result, and this is somewhat more reasoned by Brederchen and Werkinger. that gives a characterization for single crossing domain. And here, so I've read it, it's a social choice and welfare paper, so this is really beautifully written, so it's like 1.5-page proof, so I would recommend going and trying to read it, right? So it really shows how this argument proceeds, how when you try to construct single crossing ordering by combinatorial algorithm, so if obstacles arise, they correspond to one of the minors. So the minors for single crossing are slightly uglier. So one is a kind of 4x4 minor. So in fact, this is our example of profile that is single peaked but not single crossing. It's one of the forbidden minors. Remember, 2 things inside, 2 things outside. Right? So that's one of the forbidden minors. And the other one is 3x6. So I wouldn't even try to describe it. But yeah, so still they're sort of finite sized. Right? So that's a characterization from that paper. Right? So from that you can ask, okay, does one Euclidean domain admit characterization of forbidden minors? Maybe if you take minors from here and minors from there, okay, no, then you get single peaked, single crossing. Maybe if you just add something. Well, so there's another paper, so also J. Horchen, but also Kirk Prus and Gerhard Wirkinger, that says that you don't have a characterization via forbidden minors for one Euclidean preferences. Right? And it's a very technically involved result. So the way it proceeds, okay, so let me see if I can reconstruct the kind of highlight of high-level argument. So basically they say, okay, so suppose there is a characterization. So I think basically, so what they do for every number of candidates, they construct a profile that is sort of almost one Euclidean, like one step from being one Euclidean, right? And they have an infinite chain, right? So if there was a finite minor, right, so you wouldn't be able to have this infinite chain, right? So you can construct arbitrary large things that are sort of almost that are not one Euclidean, but because of just kind of one voter of one candidate, right? So if you have that sort of situation, you cannot have a characterization by finite number of small forbidden minors. Okay, so it's a complicated proof. I tried to read it because it was in J. Hor's thesis. I was on the PhD committee. Okay, so I believe I understood kind of most components, but it's like good 20 pages of heavy calculations, right? So these are easy results, right? So this is hard result and also a disappointing result, right? So there's no characterization by forbidden minors. Okay, so I think my time is up and I pretty much showed. Okay, so let me briefly talk about one more thing, right? So almost single peaked, single crossing preferences. Okay, real life preferences are very unlikely to be single peaked or single crossing. Okay, why? Because humans are, well, humans, right? So there may be, okay, so maybe, all of your voters are rational and kind of line up nicely in single crossing order, but one guy is just crazy, right? And he just orders candidates arbitrarily, right? And no matter where you stick him, he'll win the single crossing order. Or maybe one candidate is just weird, doesn't fit this left to right political ordering of candidates, right? Just has kind of political positions that are orthogonal to everything else, right? So because of that one candidate, your preference won't be single crossing. So you can ask if a given, so in fact, if you look at preference data, again, from PrefLib library, you don't see anything that is purely single peaked or single crossing. You always see noise. So you can ask if preference can be made single peaked, single crossing by, deleting a few voters, deleting a few candidates, or maybe more moderately swapping a few pairs of candidates in each vote, or kind of in total, right? So maybe you have a budget per vote, maybe you have a total budget of swaps and it's relatively small. Or maybe you can partition the voters into few groups so that each group is single peaked, single crossing with respect to their own axis, like small number of groups, 2 or 3. Right, so these are all reasonable questions. So collapsing similar candidates, right? So this is something that is known as clones, right? So because maybe some political party decides to run like 2, 3 candidates in the election, and from the voters' point of view, they all represent this party, they're indistinguishable. So voters order them randomly, and random may actually break the single peaked order, right? But still, maybe it's sort of fundamentally single peaked, right? Okay, so suppose you have preferences that maybe are like that. Can you figure it out? Can you figure out if your given input preference profile is close to being single peak, close to being single crossing? Well, that's typically NP hard, but not always. Okay, so there's a bunch of hardnesses out there. Okay, so here are some exceptions. So deleting candidates to make a given profile single peaked, right? So this is something that admits a polynomial time algorithm. Deleting voters to make a given profile single crossing, right? So that's again easy. Right, and it sort of makes sense. Candidates, single peaked is about ordering of candidates, so it's not surprising that this is easy. Deleting voters for single crossingness, this is easy. So I actually have a paper in the upcoming AAAI where we show the following. So if you have a budget of, okay, so suppose you're only allowed one swap per vote, and you want to make your preference profile single crossing, right? So you can decide that efficiently, right? And more generally, if your budget is k swaps per vote, right? So then you can do that in time that is order of kind of nm to the power k, right? Or okay, so verse, but kind of xp with respect to k, number of swaps per vote. Yes? Okay, so the rules of the game is you're allowed to shoot arbitrary k candidates. Bounded by k, yeah. Yes. Yeah, so in all these cases, so the input is a profile and a budget, like how many voters, how many candidates are allowed to delete. And we typically think of this budget as being small, so FPT algorithms with respect to that parameter are interesting already. So XP is easy, FPT is not trivial, but still interesting. Okay, so something that is sort of not hard to observe is that both of these problems can be approximated well by sort of constant factor approximation, because this is because of forbidden minor configurations. Basically, you want to kill all forbidden minors. You want to delete. So if you're in the business of deleting candidates, you want to delete candidates contributing to forbidden minors, right? And by simply deleting kind of forbidden minors as a whole, you achieve a constant factor approximation. Your constant factor is the size of that minor, so same for voters. Right, so that's an easy observation. You can do slightly better, but these minors are small, so it's a reasonable factor approximation. And now almost single-peaked, almost single-crossing can sometimes be exploited. Right, so till recently, I only had a couple of examples, but kind of as of recent ADT, kind of there's another example of this accomplishment by, well, people who are in this audience. Right, so complexity, so we didn't talk about Chamberlain-Courant yet, so that's a multi-winner rule, a rule for selecting kind of multiple candidates at the same time, a committee. Right, so this is something that can be done efficiently on almost structured profiles. So efficiently meaning XP, FPT, that type of results. Right, so also for manipulation and control, there are results of this type. Right, so generally, so almost single-peaked, single-crossing preferences are useful. Right, and this is very good news because, like I said, practical preferences are not single-peaked, not single-crossing. Right, so if you only have algorithms for single-peaked, single-crossing preference, this won't be very useful. So it's good that algorithmic results kind of extend to almost single-peaked, almost single-crossing. Okay, so I had some material on dichotomous preferences. I might talk about it in a tutorial at some point. So let me stop now. So let's have another break, and sort of at 5 we restart with Neil presenting kind of tutorial material. Okay, thanks. I'm done talking for today.